In 1998, scientists thought a mountain-sized asteroid was going to hit Earth. Within 24 hours, they changed their minds. Case closed. World moved on. But here is the part nobody tells you. The asteroid did not move on. It is still out there, crossing Earth's orbital path every single orbit, and 4 times larger than the asteroid that currently has spacecraft missions and international alarm dedicated to it. And in October 2028, it is coming closer than it has ever come in recorded history. But here's the thing. There's no radar actively watching it, no mission planned, no one checking whether the math still holds. We trusted a calculation made years ago and quietly forgot to verify it. Tonight, we open the file they closed, and what is inside might surprise you. If this has you hooked, subscribe to the Skylab, because this asteroid story is still being written, and we intend to read every page. Drop a comment below and tell me honestly, does it concern you that a kilometer-wide asteroid is arriving in 2 years and almost nobody is talking about it? Because it should probably concern someone. Let us make sure it does. Now, let's get into it. Part 1. The asteroid everyone forgot. There is a rock in space roughly the size of a small mountain. It has been crossing Earth's orbital path for millions of years, and in October 2028, it is coming back. Not metaphorically. Not as a distant blip on some theoretical chart. It is coming back in the way a freight train comes back to the same crossing, on schedule, indifferent, and enormous, and almost nobody is talking about it. The object is called 1997 XF11. That name alone tells you something. The year it was discovered is right there in the label, because nobody knew it existed before December 6, 1997. An astronomer named James V. Scotty was working with the Spacewatch telescope at Kitt Peak Observatory in Arizona, doing what asteroid hunters do, scanning the sky methodically, looking for faint moving points of light against a backdrop of fixed stars. And there it was, a new dot. A slow-moving, orbit-crossing, potentially civilization-threatening dot. Scientists classified it almost immediately as a potentially hazardous asteroid. That classification has a specific technical meaning. It means the object crosses Earth's orbital path. It means the object is large enough that if it ever connected with our planet, the consequences would be measured not in city blocks or counties, but in continents. The estimated size of XF11 sits somewhere between 0.7 and 1.4 kilometers in diameter. If you're struggling to picture that, think about it this way. A kilometer-wide rock hitting Earth at typical asteroid speeds would release energy equivalent to tens of thousands of nuclear warheads detonating simultaneously. Not one. Tens of thousands. The Chicxulub impactor that ended the age of dinosaurs was somewhere between 10 and 15 kilometers wide. XF11 would not be that, but it would not need to be. A 1-kilometer asteroid does not end all life on Earth. It ends civilization as we currently understand it. Firestorms, mega tsunamis, dust clouds that blot out sunlight for years, an impact winter that collapses agriculture globally. That is the object we're discussing. So what happened after Scotty found it? For a few months, nothing dramatic. Astronomers logged the discovery, tracked it as best they could with the limited observations available, and kept calculating. Then, in March of 1998, the International Astronomical Union made an announcement that briefly made the entire world stop. Based on the available orbital data, XF11 might pass within 30,000 miles of Earth's centre in October 2028. 30,000 miles. Earth's radius is about 4,000 miles. The Moon sits roughly 239,000 miles away. 30,000 miles from Earth's centre is not a comfortable margin. It is the kind of margin that keeps orbital mechanics experts awake at night. The media did what the media does. Headlines erupted. Scientists braced. The public, briefly, looked up at the sky with a different kind of feeling. And then, within 24 hours, the alarm was cancelled. Astronomers Paul Chodas and Don Yeomans found something remarkable. Archival photographs of the sky from Palomar Observatory, taken in 1990, showed XF11 in them. Nobody had noticed during those images originally because nobody was looking for XF11 yet. But there it was, photographed 8 years before the panic, sitting quietly in old photographic plates. Those images extended the observational arc from 88 days to 8 years. More data meant better orbital calculations. Better orbital calculations showed something reassuring. the true missed distance in 2028 would be approximately 960,000 kilometers. Safe, clear, no impact, crisis over. The world moved on. Here is the part that should bother you. The crisis was not resolved by science advancing, it was resolved by luck, by the accidental survival of photographic plates taken 8 years earlier for completely unrelated reasons. What if those plates had not existed? What if the photographs had been damaged, discarded, or simply never taken? We would have had a very different 1998. And right now, XF11 is still out there, still crossing Earth's orbital path, still carrying that same mass, that same momentum, that same indifference. The close flyby of October 2028 is confirmed. The current predicted missed distance is approximately 929,000 kilometers, about 2.4 times the distance to the Moon. The math says we are fine. But here is what nobody seems to be asking loudly enough. XF11 is up to 4 times larger than 99,942 Apophis, the asteroid that has entire spacecraft missions dedicated to it, radar campaigns, international scientific conferences, and a level of public awareness that XF11 has never received. Apophis is 370 meters wide. XF11 may be 1,400 meters wide. The larger, older, more orbit-crossing asteroid is flying past our planet in 2028, and it is not receiving a spacecraft. It is not receiving active radar. The math has not been seriously updated in years. We are trusting calculations made with data that is, at this point, getting old. We will get to why that matters in far more specific and uncomfortable detail shortly. But first, it is worth going back to those 24 hours in March of 1998, because what happened inside that brief window of global panic tells us something important about how we discover threats, how we resolve them, and how completely we forget them once the alarm stops ringing. The story of the 24-hour asteroid crisis is not just a story about a near miss. It is a story about how close we came to not knowing at all, and it raises a question that the rest of this documentary will not let go of. If we got lucky once, what are we assuming about our luck the second time? Part 2. The 24-hour asteroid crisis. On the morning of March 11th, 1998, a small number of scientists knew something that the rest of the world did not. The International Astronomical Union had just issued a circular, a formal scientific notice distributed to observatories globally, stating that asteroid 1997 XF11 had a non-negligible chance of coming dangerously close to Earth. The language was careful. Scientists are trained to be careful. But beneath the careful language was a straightforward and terrifying implication. This thing might hit us. To understand why that announcement landed so hard, you have to understand how asteroid orbits actually get calculated. When an asteroid is first discovered, scientists have a very small window of observations to work with, a short arc of the sky showing where the object has been over days or weeks. From that arc they extrapolate an orbit. The problem is that a short arc produces a wide cone of uncertainty. The asteroid could be on a slightly different trajectory than the one you calculated, and over years and decades that slight difference compounds into a completely different location in space. It is like watching a ship leave a harbour for 30 seconds and then trying to predict where it will be in 30 years. Your first guess might be close, or it might be an ocean off. When XF11 was announced to potentially pass within 30,000 miles of Earth's centre in October 2028, the orbital arc scientists were working with was approximately 88 days of observations. That is not very long. 88 days of tracking a fast-moving rock and then extrapolating its behaviour for 30 years. The uncertainty cone was significant. The possible closest approach distances ranged widely, and some of those possibilities were genuinely alarming. Not because impact was certain, it was not. But because the uncertainty band included close enough distances that even gravitational deflection during the flyby could theoretically alter the subsequent orbit into something much worse. Imagine you are throwing a ball through a narrow doorway. You believe you can thread it through cleanly, but your measurements of your throwing angle are slightly imprecise. Most of the possibilities within your margin of error still clear the door, some of them do not. That is what astronomers were facing on March 11th. And when the International Astronomical Union releases a formal circular about a potential Earth approach, people pay attention. The media did not wait for nuance. Early internet news sites, major newspapers, television networks, they ran with the story hard. The headlines were not subtle. Astronomers were suddenly doing live interviews explaining orbital mechanics to audiences who had never thought about orbital mechanics before. And here is the fascinating and slightly humbling part of the story. The scientific community itself was caught partially off guard, not because anyone was negligent, but because the system of planetary defense that exists today, coordinated, funded, institutionalized, was still being built in 1998. The awareness had been growing, but the infrastructure was young. Then Paul Chodas and Don Yeomans, working at NASA's Jet Propulsion Laboratory, did something that seems almost mundane in retrospect. They asked whether pre-discovery images of XF11 might exist somewhere in photographic archives. This was standard practice, but it required someone to actually go and look. Eleanor Helen, a veteran asteroid hunter, located images of the sky region taken at Palomar Observatory in 1990. Those plates, 8 years old, showed XF11 before anyone knew it was XF11. A faint dot in the right place, on the right date, waiting to be found by someone who knew what they were looking for. The effect of those images on the orbital solution was dramatic. Extending the observation arc from 88 days to roughly 8 years transformed the uncertainty cone from alarming to manageable. The revised closest approach distance in 2028 was 960,000 kilometers, not 30,000 miles, not dangerously close, safe. The announcement went out, the alarm was cancelled, the world exhaled and moved on to the next story. What very few people processed in the aftermath was the fragility of that resolution. Those Palomar plates existed because routine sky survey programs had been running for decades. They were found because someone thought to look. They were usable because they had been stored carefully. Remove any one of those variables and the story of 1998 ends differently. Without those plates, the orbit remained uncertain. Without a certain orbit, planetary defense agencies faced a real and open question about a real and close asteroid approach 30 years in the future. The science did not save us. The archive did. Lucky record keeping by astronomers who had no idea they were creating a future safety net. That ought to feel uncomfortable, and there is a reason to linger on that discomfort. Because the lesson of the 1998 crisis is not that the system worked. The lesson is that the system almost did not work, and what saved it was luck masquerading as methodology. So here is the question that starts to form. XF11 is returning in 2028. The orbital solution is considered resolved, but resolved on the basis of data that is now decades old, with a last meaningful radar observation from 2016, and with a set of physical properties, rotation, composition, surface texture, that remain only partially characterized. We trusted luck once. What exactly are we trusting now? Part 3. The asteroid that quietly became dangerous again. Let us set aside the 1998 panic for a moment and talk about something that sounds technical but matters enormously. It is called the minimum orbit intersection distance, and for 1997 XF11, that number is effectively zero. Zero. Not close to zero, not nearly zero, zero. What that means, in plain terms, is that XF11's orbit and Earth's orbit intersect. They cross. The asteroid's path through space physically passes through the same region of space that Earth travels through every year. The fact that a collision has not happened yet is a matter of timing. Earth and XF11 simply have not been at that intersection point simultaneously, but they keep trying. Every 633 days, that is XF11's orbital period, 1.73 years, the asteroid completes another loop around the Sun and crosses Earth's orbital path again. It has been doing this for an extraordinarily long time. It will continue doing this for an extraordinarily long time into the future. We just happen to be the generation living through the particularly interesting chapter where the approaches are getting close enough to notice. XF11 is an Apollo-class asteroid, which is the classification given to near-Earth objects with orbital periods greater than 1 year that cross Earth's orbit. Apollo-class asteroids are the most immediately relevant category when planetary defense scientists think about impact risk. XF11's orbit takes it as close to the Sun as 0.74 astronomical units at perihelion, that is closer to the Sun than Venus, and as far out as 2.14 astronomical units at aphelion, which puts it past Mars. Every orbit it swings past the inner solar system, crosses Earth's path and heads back out. Over and over on a 31-year track record of human observation. We have watched it do this repeatedly. Here is something that should recalibrate your sense of how well we understand our own cosmic neighbourhood. XF11 passed relatively close to Earth in 1957. It passed relatively close again in 1971. Nobody knew. There was no Spacewatch program in 1957. There were no systematic near-Earth asteroid surveys. The asteroid was flying past our planet while humans were launching Sputnik and worrying about nuclear weapons, and nobody had any idea it existed. That is not ancient history. That is within living memory. A mountain-sized rock making close passes to Earth, and we had not the slightest awareness of it. This realization prompted a significant expansion of asteroid detection programs after the 1998 XF11 scare. The combination of public attention, congressional inquiries, and genuine scientific alarm accelerated investment in sky surveys. Programs like Linear, NEAT, and later Catalina Sky Survey began cataloguing near-Earth objects at a rate that was simply impossible with older technology. The XF11 panic was, in a roundabout way, good for planetary defence. It forced a conversation that needed to happen. But here is the part of the story that introduces the long, slow complication. Orbital mechanics over long timescales is not a simple clockwork system. It is a gravitational conversation between multiple bodies, the Sun, the planets, the asteroid itself, and that conversation is fundamentally chaotic. Not chaotic in the casual sense of disorganized, chaotic in the precise mathematical sense. Tiny differences in initial conditions produce dramatically different outcomes over time. Every time XF11 passes close to Earth or another planet, gravity tugs at it slightly. The orbital period changes by a small amount. The inclination shifts fractionally. The perihelion distance adjusts. Each of these changes is individually tiny. Across decades and centuries, they accumulate into something much harder to predict. This is where the 2028 flyby becomes more than a curiosity. When XF11 passes Earth at approximately 929,000 kilometers in October 2028, Earth's gravity will interact with the asteroid. The effect will be small, but small is not zero. The orbital period will shift. The subsequent orbital path will be subtly different from what it was before the flyby, and where the asteroid ends up after that depends on exactly how that flyby unfolds, which depends on precise knowledge of the current orbit, which depends on how well we have been tracking it. We are now approaching something that the planetary defense community understands, but that rarely makes it into public discourse. The 2028 flyby is not the last chapter of the XF11 story. It is, in a very real sense, the beginning of a new and more complicated one. What happens after October 2028 is a question that requires data we do not yet have, and the window to gather that data is closing in a way that has not prompted nearly the urgency it deserves. The math says we are safe, but the math is only as good as the measurements feeding it, and those measurements have a timestamp that is getting harder to ignore. Part 4, the size problem nobody talks about. Here is a number that should stop you. If XF11 is at the upper end of its estimated size, 1.4 kilometers in diameter, and Apophis, the asteroid that has captured global scientific and media attention for 2 decades, is approximately 370 meters wide, then XF11 is not just somewhat bigger, it is not double the size. The volume of a sphere scales with the cube of the diameter. Do that math and XF11 could be nearly 40 times the volume of Apophis. 40. And yet Apophis has spacecraft missions. Apophis has radar campaigns. Apophis has an entire international scientific community monitoring it with dedicated resources. XF11 has a last radar ping from 2016. Impact energy is not a linear function of size. It scales with mass, and mass scales with volume. A rock that is 4 times wider than another rock, assuming similar densities, carries roughly 64 times the kinetic energy. When planetary defense scientists talk about Apophis as a serious threat worth dedicated resources, they're talking about a 370-meter object with an energy potential already large enough to devastate a continent. Scale that up to a potential 1.4-kilometer object, and you're talking about something qualitatively different. You are talking about an event that disrupts the global climate system, collapses agricultural output across multiple growing seasons, triggers cascading infrastructure failures, and kills not millions but potentially billions of people indirectly. Not in the immediate impact zone. globally, through the aftermath. Let us put some numbers to this. The Tsar Bomba, the largest nuclear weapon ever detonated by humans, released approximately 50 megatons of energy. A 1-kilometer asteroid striking Earth at a typical impact velocity of around 20 kilometers per second would release somewhere in the range of 10,000 to 100,000 megatons of equivalent energy, depending on composition and angle. That is 200 to 2,000 times the largest nuclear weapon ever built, detonating in a single point, creating a crater perhaps 20 to 30 kilometers wide, sending a shock wave that destroys structures for hundreds of kilometers in every direction, ejecting debris into the upper atmosphere globally. This is not science fiction. This is physics applied to a rock we have been watching for 27 years and mostly stopped worrying about. To be precise, XF11 is not the Chicxulub impactor. The Chicxulub asteroid was somewhere between 10 and 15 kilometers wide. It released energy on a scale that is almost incomprehensible. Roughly 1 billion megatons. It ended the non-avian dinosaurs. It caused a mass extinction event that wiped out approximately 75% of all species on Earth. XF11 is not in that league. What XF11 is what scientists call a civilization-threatening asteroid. Not a species-ending event. A civilization-ending event. There is a meaningful difference, and it is worth being clear about it. But calling something civilization-threatening is not reassurance. It is a description of a category of disaster for which human history has absolutely no precedent, no recovery playbook, and no institutional memory. The paradox here is institutional and psychological. Apophis passes Earth at 31,000 kilometers in April 2029, inside the orbital ring of geostationary satellites. That is extraordinary proximity. It is visually dramatic. It is the kind of number that makes people lean forward. XF11 in 2028 passes at 929,000 kilometers. That sounds safe by comparison. And in terms of immediate impact probability, it is safe. The current probability of XF11 hitting Earth in 2028 is 0, not negligible, 0. So the question becomes, why study it? The answer is that proximity in a single flyby is not the only relevant metric. Repeated orbital crossings over centuries, combined with size, combined with unmeasured physical properties that affect long-term orbital evolution, combined with a Yarkovsky drift that has never been characterized, these factors together create a different kind of risk profile than Apophis presents. Apophis is a closer threat on a shorter timeline. XF11 is a larger, longer-term uncertainty that the current scientific prioritization system is structurally not well designed to address. We have built our planetary defense attention budget around immediate proximity, and that makes a certain kind of logical sense. It also means a mountain-sized asteroid is heading for its closest approach in living memory, and the scientific community's response is essentially, we checked the math a few years ago, and it looked fine. Did anyone think to ask when the math gets checked again? Part 5. The 2028 flyby. Mark the date. October the 26th, 2028. On that day, asteroid 1997 XF11 will make its closest approach to Earth since before recorded human history, passing at approximately 929,000 kilometers, or about 2.4 times the distance from Earth to the Moon. If you have a decent pair of binoculars, you may actually be able to see it. Estimates suggest it will reach approximately magnitude 8 at closest approach, which puts it at the threshold of naked eye visibility under very dark skies and easily within reach of amateur telescopes. A mountain-sized rock, visible in the night sky. There is something both beautiful and mildly unsettling about that image. From a purely observational standpoint, the 2028 flyby is an opportunity. Close approaches create optimal windows for radar observation, and radar observation is what turns orbital guesswork into genuine precision. When an asteroid passes close enough, facilities like the Goldstone Solar System radar in California or the Arecibo-class systems, where they still exist, can bounce radio waves off the surface and receive the return signal. The delay time tells you distance. The Doppler shift tells you velocity. The pattern of the return signal, analysed carefully, tells you shape, spin rate, and surface characteristics. One good radar campaign during a close approach can shrink orbital uncertainty by orders of magnitude. It can also tell you things about the asteroid's physical nature that are essential for understanding its long-term orbital evolution. Radar is important here for a reason that goes beyond simple tracking. Every asteroid larger than a few hundred meters has what is called a Yarkovsky effect acting on it, a tiny but real force generated by sunlight heating the surface unevenly. Sunlight hits the day side, the asteroid rotates. The heated surface radiates thermal energy slightly off-center from the direction of incoming light, and the net effect is a tiny but persistent thrust. Over decades, that thrust moves the asteroid. The direction and magnitude of the drift depend on the asteroid's rotation axis, its surface composition, its thermal conductivity, all things you can begin to characterize with good radar data. Without radar data, you're essentially guessing at a parameter that meaningfully affects where the asteroid will be in 20, 30, 50 years. XF11's last dedicated radar campaign was in 2016. The 2028 flyby would be the next natural opportunity to update that data. Whether anyone is planning to use that opportunity is, at this point, genuinely unclear. Here is where the physics becomes philosophically interesting. The 2028 flyby is not gravitationally neutral. When XF11 passes Earth at 929,000 kilometers, Earth's gravity will apply a small but real torque to the asteroid's orbit. Brian Marsden, one of the most respected orbital mechanicians in the history of the field, analysed XF11's orbital future in the late 1990s and found that the post-flyby orbital period could shift to anywhere between 1.53 and 1.99 years, depending on the precise geometry of the encounter. That range might sound technical, but it has real consequences. Different orbital periods lead to different resonance relationships with Earth's orbit. Some of those resonances produce repeated close encounters. Some of those repeated close encounters, depending on precise initial conditions, produce trajectories that cross Earth's path at moments when Earth is there too. To be completely clear, current orbital models show no impact threat from XF11 in 2028, or in the foreseeable future after that. The planetary defense community is not privately alarmed and publicly silent. The scientists who study this are not hiding something. The assessment is genuine, but there is a meaningful difference between current models show no threat and we have definitively characterized this asteroid's long-term behavior. The first is a statement of current knowledge. The second would require measurements that have not been made. And what we know from the mathematics of chaotic systems is that small uncertainties in current conditions, the kind that accumulate when you go years without fresh radar data, can propagate into large uncertainties in future orbital positions. The models are only as good as the inputs. The inputs have an expiration date, and the expiration is approaching faster than the mission planning process can accommodate. So here is the open question this flyby leaves us with. We have one of the largest known near-Earth asteroids making its closest approach in history on a specific known date. We have a physical mechanism that will alter its orbit during that flyby. We have a well-understood scientific technique that could dramatically improve our long-term orbital model of this object. And we have, as far as current public information shows, no dedicated mission or campaign planned to take full advantage of this window. Why not? That question does not have a comfortable answer. And the next part of this story suggests the discomfort is more than just bureaucratic. Part 6. The Post-28 Chaos Problem. Imagine you're standing at a fork in a river, watching a large piece of debris drift toward it. You can calculate which channel it will enter if you know its exact speed and position. But your measurements have a small error margin. In the near channel, the debris floats safely out to sea. In the far channel, it hits a dam. Small measurement uncertainty, large consequence difference. That is, in compressed form, the mathematical situation that XF11 presents after its 2028 flyby. Orbital mechanics operates on principles that are deterministic in theory, but chaotic in practice. Given perfect knowledge of an asteroid's position and velocity at one moment, you can calculate its position at any future moment with perfect accuracy, in principle. In practice, your knowledge is never perfect. Measurements have tolerances, models have assumptions, and when you project forward in time, the uncertainty in your starting conditions grows. The further you project, the wider the uncertainty cone becomes. For an asteroid that will experience a gravitational perturbation during a close flyby, that cone can widen dramatically depending on how the flyby unfolds. Brian Marsden's analysis of XF11 in the late 1990s showed that after the 2028 flyby, the asteroid's orbital period could shift to values ranging roughly between 1.53 and 1.99 years. This is not a trivial range. The orbital period determines which resonance relationships develop between XF11 and Earth over subsequent decades. Orbital resonance occurs when the ratio of orbital periods between two objects simplifies to a small fraction of integers. When that happens, the two objects repeatedly encounter each other at similar points in their orbits, and gravitational interactions compound over time rather than averaging out. Resonances can be stable, they keep objects separated. Or they can be destabilizing, they gradually nudge an object toward more dangerous trajectories. Marsden identified two resonance possibilities that warranted attention. A 9-to-5 resonance could produce a potentially concerning encounter in 2037. A 12-to-7 resonance pointed toward 2040. The early models for these scenarios, before the 1990 data was incorporated, showed some orbital trajectories passing very close to Earth. After the extended observational arc resolved the orbit more precisely, those specific trajectories were ruled out. The orbital solution became much tighter. The alarming possibilities were eliminated for the orbit as it was then calculated with the data then available. That final qualifier carries weight, the orbit as it was then calculated, with the data then available. Those words are doing real work in that sentence. Since Marsden's analysis, XF11 has completed multiple orbits around the Sun. Every orbit, small forces act on it. The Yarkovsky effect applies its tiny thermal thrust, pushing the asteroid slightly away from the orbit the models predict. Gravitational interactions with other bodies, not just Earth but Mars, Jupiter, Venus, apply small cumulative torques. The asteroid is not following a theoretical line through space. It is being nudged constantly in ways that accumulate over years. Our last radar observation was in 2016. Between 2016 and 2028, the asteroid will have completed approximately 8 orbits around the Sun. 8 orbits during which the Yarkovsky drift and gravitational perturbations from multiple planets will have moved it some fraction further from where our models expect it to be. At the level of determining whether XF11 hits Earth in 2028, the current orbital solution is robust. The miss distance has a comfortable margin. But at the level of determining which post-flyby resonance relationship develops and what that implies for encounters in 2037 or 2040, the precision requirements are dramatically higher. The difference between a 9-to-5 resonance and a 12-to-7 resonance, in terms of the orbital period that produces them, is small. The consequences for long-term trajectory are not small, and the measurement precision needed to distinguish between these outcomes requires data that, as of this writing, we do not have. The remarkable thing is that this is not a secret. These considerations are documented in the scientific literature. Orbital chaos is a well-understood phenomenon. The dependency of post-flyby trajectories on precise flyby geometry is a well-understood problem. The people who work on planetary defense know all of this. And yet the operational response, the actual scheduling of observations, the allocation of telescope time, the planning of radar campaigns, has not matched the scientific understanding of what is at stake. We understand that something important is happening in October 2028, that the outcome of that flyby will determine XF11's orbital trajectory for decades, and that characterizing that outcome requires measurements we have not yet made. Somewhere between understanding the problem and mobilizing the resources to address it, something is getting lost. What that something is takes us directly into the next uncomfortable question. Part 7. The Yarkovsky drift nobody measured. In the early 20th century, a Polish engineer named Ivan Osipovich Yarkovsky proposed something that sounded almost absurd at the time he proposed it, in an era when the mechanisms governing the solar system were considered largely settled, and the idea that sunlight could meaningfully push a rock around in space sat uncomfortably close to the boundary between careful scientific speculation and something that would not survive peer review. Yarkovsky's suggestion was specific and physical rather than vague and mystical, which is what makes it interesting in retrospect. He was not proposing anything that violated known physics. He was pointing out a consequence of known physics that everyone else had been too focused on gravity to notice. Sunlight, he argued, could over very long periods meaningfully change the orbit of a small body in space. Not through gravitational attraction. The gravitational pull of sunlight on an asteroid-sized object is so negligible as to be unmeasurable with any instrument available in the early 20th century or for decades afterward, through something subtler, through the momentum carried by thermal radiation, through the slow, continuous asymmetric push of a process so gentle that it takes years to produce measurable displacement and decades to produce displacement that matters for orbital prediction. Through what amounts, if you want a working metaphor, to a thermal jet engine powered by the sun and running without any moving parts, any fuel, or any mechanism that anyone had thought to account for in orbital calculations. The physical process Yarkovsky identified works like this. Sunlight hits the surface of a rotating asteroid and heats it. The asteroid continues rotating. Hours later, the exact delay depending on the thermal properties of the surface material, how quickly it absorbs heat and how quickly it radiates it back out. The now heated surface has rotated away from the direction of incoming sunlight and faces a different direction in space. That heated surface radiates thermal energy as infrared photons in the direction it now faces. Those photons carry momentum. By Newton's third law, the emission of those photons in one direction produces a reaction force in the opposite direction. The net result, integrated over the entire surface of the rotating asteroid across the full cycle of its rotation and its orbit around the Sun, is a tiny but real and continuous thrust acting on the asteroid in a direction that depends on the orientation of its spin axis relative to its orbital plane. The force is small. For a kilometer-class asteroid, we're talking about a thrust comparable to the weight of a few sheets of paper, but it acts continuously, without interruption, across years and decades and centuries. Small forces applied continuously over long times produce large displacements. This is the mathematical structure of the Yarkovsky effect, and it is why an idea that sounded almost whimsical in the early 20th century became one of the most important factors in long-term asteroid orbital prediction by the end of the 20th century. Yarkovsky's proposal was largely forgotten after his death, partly because the precision of orbital measurements available during his lifetime was nowhere near sufficient to detect the effect he was describing, and partly because the field of asteroid science as we currently understand it did not yet exist in a form that would have found the idea immediately useful. The rediscovery of the Yarkovsky effect as a practically important phenomenon came gradually in the latter half of the 20th century, accelerating as radar astronomy developed the capability to measure asteroid positions with the precision needed to detect orbital deviations at the level the effect produces. By the 1990s and 2000s, the Yarkovsky effect had moved from theoretical curiosity to observational target, and the most famous and consequential demonstration of its real-world importance involves an asteroid named 101,955 Bennu, the target of NASA's OSIRIS-REx sample return mission, and, until the mission's detailed characterization work substantially revised the risk picture, one of the more carefully watched potentially hazardous asteroids in the catalogue. Radar measurements of Bennu, accumulated over more than a decade of dedicated observation campaigns, tracked the asteroid drifting from its gravitationally predicted orbital position by 160 kilometers over 12 years. 160 kilometers, the length of a major metropolitan area, measured as a deviation from where Bennu would have been if only gravity were acting on it. The Yarkovsky effect, sunlight heating a rotating surface and the delayed thermal emission producing a continuous tiny thrust, had moved Bennu by a city's length in just over a decade of operation. When scientists incorporated the measured Yarkovsky drift into Bennu's long-term orbital models, the consequences were not trivial. The impact probability assessments changed. The specific future dates that carried elevated risk changed. The overall picture of Bennu's long-term threat potential shifted in ways that were scientifically significant and practically important for planetary defense planning. Without the measurement, the models were wrong. Not approximately right with small errors, systematically wrong in a specific and quantifiable direction, producing incorrect probability estimates for specific future dates, because a real physical force was operating on the asteroid that the models were not accounting for. The lesson was clear and should have been broadly applied. For any asteroid whose long-term orbital behavior matters for planetary defense purposes, the Yarkovsky drift is not an optional refinement. It is a necessary measurement. Now consider what this means for 1997 XF11. The Yarkovsky effect on any given asteroid depends on several physical parameters that vary from object to object and that cannot be assumed without measurement. The orientation of the spin axis relative to the orbital plane determines the direction of the Yarkovsky thrust, whether it pushes the asteroid outward from the Sun or inward, speeding its orbit or slowing it. The thermal conductivity of the surface material determines the delay between solar heating and thermal emission, which determines the precise geometry of the thrust direction. The density and bulk composition of the asteroid affect how the thermal wave propagates through the surface layer. The albedo determines how much sunlight is absorbed in the first place rather than reflected. All of these parameters interact to determine the net Yarkovsky acceleration, and none of them can be reliably inferred from first principles for a specific object. They must be measured. For larger asteroids, the effect is generally smaller in relative terms. This is a real and important physical point that should be stated accurately. As an asteroid grows larger, its mass increases with the cube of its diameter, while its surface area increases only with the square. More mass, proportionally less surface to receive sunlight and emit thermal radiation, means less Yarkovsky acceleration per unit mass. A kilometer-class asteroid experiences less Yarkovsky drift per year than a 100-meter asteroid of similar composition would. This is why some scientists are genuinely less concerned about Yarkovsky uncertainty for XF11 than they would be for a smaller object. The concern is proportionally reduced. The physics supports that assessment as a general statement. But the relevant question for XF11 is not the general statement. The relevant question is whether the Yarkovsky effect on this specific object is small enough, over the specific time horizon and to the specific precision required for the post-flyby resonance analysis, to be safely treated as negligible without measurement. And the honest, complete, unhedged answer to that question is one that the scientific community has not been able to give because the measurement has not been made. The Yarkovsky drift for XF11 has never been directly characterized. Unlike Bennu, which received multiple dedicated radar campaigns, and ultimately a spacecraft that measured its physical properties at close range, XF11 has been observed with radar exactly once in its entire known history. One campaign, conducted at the Goldstone Solar System radar facility in 2016. A single campaign, nearly a decade before the close flyby that the drift measurement would most directly inform, for a 1-kilometer object with a minimum orbital intersection distance of effectively 0, an orbital period that crosses Earth's path every 1.73 years, and a major flyby approaching in October 2028, whose precise geometry will determine the post-flyby trajectory for decades. One radar campaign conducted nearly a decade in advance is not an adequate observational foundation for high-confidence long-term orbital prediction. The word that appears in the scientific community's published assessments of the Yarkovsky situation for XF11 is likely. The effect is likely small. That single word is carrying weight far out of proportion to its apparent modesty. Likely is not measured. Likely is not characterized. Likely is a reasonable inference from known physics applied to an object of this size class, without specific knowledge of the spin axis orientation, the surface thermal properties, or the compositional details that actually determine the magnitude and direction of the effect for this specific object. Likely is what you say when you have not measured something, but you have good physical reasons to expect it, falls within a certain range. For an object that, in the scenario where the orbital models turn out to be wrong in the specific ways that would matter most, could produce encounters with Earth in the 2037 to 2040 timeframe. Likely is a word that deserves to be replaced with measured. The gap between those two words is a radar campaign. It is the difference between an assumption and a fact, between a model that incorporates a physical effect and a model that characterizes it. The compounding structure of the uncertainty is what makes the unmeasured Yarkovsky drift specifically problematic rather than merely incomplete. The force does not produce a sudden jump in the asteroid's position. It accumulates slowly, continuously, in a direction that has not been well characterized for XF11. Over the 8+ years since the 2016 radar campaign, the asteroid has been drifting from its predicted orbital position by some amount. The drift is possibly small. It is not zero. That drift introduces a small additional uncertainty into the predicted geometry of the 2028 flyby. The flyby geometry uncertainty propagates into uncertainty in the post-flyby orbital period. The orbital period uncertainty propagates into uncertainty about which resonance relationship develops between XF11 and Earth's orbit in the subsequent decades. and the resonance relationship determines the character of encounters in 2037, 2040, and the decades beyond that. Tiny uncertainties, long-time horizons, consequences that are not small. This is the mathematical architecture of the problem, and it has a known solution that requires a radar, a schedule, and the institutional will to treat an unmeasured physical parameter as the priority that the science clearly indicates it should be. Part 8. The monitoring gap. Here is a comparison that makes the point more sharply than any abstract argument could. Apophis, the 370-metre asteroid that passed uncomfortably close in the public imagination for most of the 21st century's first 2 decades, received dedicated radar observations in 2005, 2012, 2013, and 2021. 4 separate radar campaigns across 16 years. Each campaign refined the orbital solution. Each campaign updated the Yarkovsky drift measurement. Each campaign narrowed the uncertainty cone for the 2029 flyby and the subsequent decades. By the time Apophis makes its close approach in April 2029, it will be one of the best characterized asteroids in the solar system. Scientists will know its shape, spin state, composition proxies, and orbital parameters to extraordinary precision. XF11 has approximately 2,243 recorded observations spanning from 1990 to 2023. It had 1 radar campaign, conducted at Goldstone in 2016. There is no publicly announced follow-up radar campaign scheduled before the 2028 flyby. There is no spacecraft mission in development or planning. The asteroid that is potentially 4 times larger than Apophis, with an orbital crossing point at 0 minimum intersection distance, arriving for its closest Earth approach in history, is being monitored with essentially passive optical observations and data that is approaching a decade old. Why does this gap exist? The answer is not simple, and it is not a story of negligence or incompetence. The planetary defense community is small, chronically underfunded relative to the scale of the problem it addresses, and operating within institutional constraints that were designed for a different era of asteroid awareness. Large radar facilities like Arecibo, which was arguably the most powerful planetary radar system ever built and was essential to XF11's 2016 campaign, no longer exist after the catastrophic collapse in December 2020. Goldstone remains operational, but it has a finite observation schedule and faces competition from many scientific programs for time. The calculus of which asteroids get radar campaigns is driven by immediacy of risk, objects with near-term impact probabilities, objects that are about to become inaccessible to observation, objects with specific scientific questions that only radar can answer. XF11, with its confirmed safe 2028 flyby and its long-term uncertainties that are concerning but not immediately alarming, does not score highly on any of those criteria individually. The immediate risk is 0. The scientific questions are real but not uniquely urgent in any given week. So it falls through the cracks of a prioritization system that was not designed to flag diffuse, long-term, cumulative risk from large objects with well-resolved but aging orbital solutions. The system is not broken, it is working as designed. The question is whether the design is adequate for the problem. The data that does exist for XF11 is publicly available. JPL's Horizon system, the Minor Planet Center, NASA's Center for Near-Earth Object Studies. These repositories contain the full observation history, orbital parameters, and uncertainty estimates. Any researcher with appropriate expertise and computational resources can access this data and run their own orbital propagations. The transparency is genuine and admirable, but transparency about existing data is different from a commitment to gathering new data. The public availability of a 2016 radar solution is not a substitute for a 2024 or 2025 radar campaign. There is also a question of mission architecture. If you wanted to send a spacecraft to XF11, not to deflect it, simply to characterize it, the 2028 flyby creates a gravitational geometry that is actually favorable for mission planning. A spacecraft launched on an appropriate trajectory could rendezvous with or fly by the asteroid during the same window it passes close to Earth, taking advantage of reduced delta-v requirements. Mission planning for something like this typically requires 5 to 10 years of lead time. The current moment, 2026, is approximately at the edge of the window, where a dedicated characterization mission to XF11 for the 2028 approach remains plausible. If the decision to fly has not been made yet, it almost certainly will not happen in time. The window is not closed, but it is closing, and nobody in a position of decision-making authority appears to be watching the clock. Part 9. The Lucky Photograph Problem. In 1990, astronomers at Palomar Observatory pointed their telescope at various patches of sky as part of routine sky survey work. They were not looking for XF11. Nobody knew XF11 existed. They were doing the unglamorous, essential, methodical work of documenting the sky, capturing images on photographic plates that would be archived, catalogued, and stored. At the time, this work generated no headlines. It attracted no public interest. It was not funded by the fear of asteroid impacts or the urgency of planetary defense. It was funded by the general recognition that comprehensive sky surveys have scientific value for many different purposes, most of them having nothing to do with rocks that might one day threaten civilization. The astronomers doing this work were not heroes in any dramatic sense. They were technicians of the sky, doing their jobs carefully and without fanfare, building an archive that nobody yet knew would matter. The photographs sat in storage. 8 years later, when panicked orbital calculations suggested a mountain-sized rock might be heading for Earth, someone thought to look through old photographs and found XF11, previously uncatalogued, previously unmeasured, sitting patiently in images from 1990. That accidental archive saved the orbital solution. That is the story, and it is a story worth generalizing far beyond the specific case of XF11. The concept of pre-discovery observations is familiar to asteroid astronomers, even if it sounds almost paradoxical to everyone else. How do you discover something that was already photographed? The answer is that discovery, in this context, means recognition rather than first imaging. Most newly discovered near-Earth asteroids, when their orbital positions are backtracked through existing sky survey archives, turn out to have been photographed multiple times before anyone identified them as asteroids. They were present in the images, but they were simply unrecognized, lost among the hundreds of thousands of other faint points of light captured in any given sky survey frame. The sky has been photographed comprehensively for decades. Those photographs contain information about objects that nobody was looking for at the time of capture, objects that were crossing their orbital paths, making their quiet approaches, completing their loops around the sun, while human civilization went about its business entirely unaware. Mining that archive has repeatedly produced valuable pre-discovery data that dramatically improves orbital solutions for newly discovered objects. The practice is established, scientifically important, and increasingly being automated using machine learning algorithms that can identify faint-moving objects in archival images faster and more reliably than human review ever could. But the 1998 situation with XF11 reveals a fragility in this system that deserves more attention than it typically receives. The resolution of that crisis depended on three conditions holding simultaneously. The pre-discovery data existed, it was findable, and it was usable. All three were true, and the orbital crisis was resolved within 24 hours of the initial alarm. Remove any one of those conditions and the story ends in a completely different place. Consider what might have happened if the survey program that produced those 1990 plates had been cancelled in 1988 for budget reasons, as many sky survey programs were cancelled during that era of scientific austerity. The plates would not have existed. The extended observation arc would not have been available. The orbital uncertainty would have remained unresolved. Consider what might have happened if those plates had been improperly stored and had degraded beyond usability, which was not an uncommon fate for photographic archives of that era, when the long-term preservation of astronomical data was not treated as a priority. Consider what might have happened if the search for pre-discovery data had not been initiated quickly enough, and the announcement of a potential impact had been allowed to stand uncorrected for weeks rather than hours, allowing public alarm to compound and the scientific community to become publicly committed to a position that was subsequently difficult to walk back gracefully. None of these near misses actually happened. The plates existed. They were stored properly, they were found in time. The crisis was resolved cleanly and the world moved on. But the fact that things went well does not mean the system that produced the good outcome was robust. It means the system was lucky. There is a meaningful difference between a robust system and a lucky one, and the history of asteroid detection is full of moments where luck and robustness are difficult to distinguish from the outside. surveys that were funded or not, telescopes that were built or not, photographic plates that were stored carefully or not, archivists who maintained institutional knowledge about where old data was kept or retired without passing that knowledge on. Each of these contingencies represents a branch point where the outcome depended on choices and circumstances that had nothing to do with the scientific importance of the data being preserved. The system that saved us in 1998 was not designed to save us. It was designed to do astronomy. Saving us was a side effect. The systematic improvement of planetary defense capabilities in the decades since 1998 has reduced some of these contingencies in ways that are genuinely significant. More sky is being imaged more frequently than at any previous point in history. Digital imaging has replaced photographic plates entirely for modern survey work, producing instantly searchable, redundantly backed up, globally accessible data rather than physical archives stored in a single location and vulnerable to all the hazards that physical objects face. Automated detection algorithms flag moving objects in real time, removing the dependency on human reviewers who might miss a faint point of light at the edge of a crowded frame. The infrastructure for discovering, tracking, and archiving near-Earth asteroid data is meaningfully better than it was in 1998 in ways that are not merely incremental but structural, and yet the asteroid population remains large, and the discovery completeness for the most consequential size ranges remains far below what planetary defense requires. Near-Earth asteroids in the 100 to 500 meter size range, objects large enough to destroy a country, generate devastating tsunamis, or produce civilization-disrupting climate effects through the dust and debris their impact would inject into the atmosphere, are still substantially uncatalogued. Estimates from the mid-2020s suggest that less than half of the estimated population of near-Earth objects larger than 140 meters has been identified. That is the midpoint of the dangerous medium range, below 50% discovered, which means for every known Apophis, for every catalogued, tracked, regularly observed object with an assigned risk profile and a Torino scale rating, there may be dozens of equally dangerous objects crossing Earth's orbital path on schedules we cannot know because we do not know the objects exist. They have no catalogue entry. They have no orbital solution. They have no pre-discovery photographs waiting to be found because no survey has yet captured them in a recognisable way. They are simply out there, completing their orbits, indifferent to the gap in our knowledge that their existence represents. The 1997 XF11 scenario was, in a retrospective sense, a rehearsal for a harder version of itself. XF11 had the saving grace of old photographic plates. The next significant unknown asteroid may not, an object discovered for the first time on a short observational arc without archival pre-discovery data to extend the solution, presenting an alarming preliminary orbital calculation, would put the 1998 situation on a much harder difficulty setting. The tools for resolving the uncertainty would be fewer. The time available for gathering new observations might be limited. The margin for error in the communication of a risk to the public and to policymakers would be narrower. The system that handled XF11 in 1998 would face the same test with worse conditions and higher stakes. The honest assessment of where planetary defense stands in the mid-2020s requires holding two things simultaneously, without allowing either to cancel the other out. The infrastructure has improved enormously, and the people building and operating it are doing extraordinary work with the resources available to them. The gap between what currently exists and what a genuinely comprehensive planetary defense system would require remains significant, specific, and in several areas well characterized enough that the scientific community knows exactly what is missing and what filling those gaps would cost. Pre-discovery observation programs that cover the full sky at the sensitivity needed to detect sub-kilometer objects. Comprehensive sky surveys running on cadences fast enough to catch fast-moving objects that older surveys would miss between observation epochs. Archive digitization projects that make decades of historical sky survey data accessible to modern AI-assisted search algorithms. These are not speculative future technologies. They are known investments with understood returns. They pay off not in the week they are funded, but in the decade when an unknown asteroid turns out to have been photographed 20 years ago by a survey program that someone, at some point, chose to fund and maintain. You do not know in advance which investment will matter. The astronomers at Palomar in 1990 did not know their routine sky survey would become the data point, that resolved a global crisis 8 years later. Nobody knows which archive will contain the pre-discovery data for the next XF11, or whether that archive will exist when the moment of need arrives. You invest broadly. You archive carefully. You build systems designed not just for the science you're currently doing, but for the science you cannot yet anticipate needing. You treat the unglamorous, methodical work of documenting the sky as the irreplaceable infrastructure it actually is, rather than the fundable when convenient line item it has historically been treated as. That is the logic of planetary defense, not heroic response, patient, continuous preparation. And that logic is, right now, being tested in ways that most of the public is not aware of, by an asteroid that has a close approach in October 2028, and an orbital solution that nobody has seriously updated in years. The archive saved us once. Whether it saves us again depends on choices being made right now, in budget meetings and mission planning sessions and observatory scheduling discussions that will never make the news, until they have to. Part 10. The real threat is not XF11. NASA estimates that more than 95% of near-Earth asteroids larger than 1 kilometer in diameter have now been discovered. Read that sentence again because it contains something remarkable that is easy to absorb too quickly and too casually. In roughly 30 years, from the early 1990s to the present, the planetary defense community went from knowing almost nothing about the large near-Earth asteroid population to having identified the vast majority of it. Think about what that actually required. New telescope technologies designed specifically for the task of finding faint, fast-moving objects against crowded star fields. New automated detection software capable of processing volumes of imaging data that would overwhelm any human review team. New orbital calculation pipelines that could take a handful of observations spanning days and produce a preliminary orbital solution within hours. New international coordination frameworks that allowed observatories on different continents to share data, divide sky coverage, and collectively build a catalogue that no single institution could have assembled alone. And sustained political will to fund all of it across multiple administrations, multiple budget cycles, multiple shifts in scientific priority, across 3 decades during which the immediate urgency of the asteroid threat was never constant, and the temptation to redirect funding elsewhere was always present. It worked. The large asteroid problem is, to a significant degree, a solved problem in terms of discovery. That achievement deserves genuine recognition before the caveats begin, and the caveats are coming. 95% is not 100%. That gap, which sounds almost negligible when expressed as a percentage, represents something considerably less negligible when you work out what it means in absolute terms. The estimated population of near-Earth asteroids larger than 1 kilometer sits somewhere between 900 and 1,000 objects. 5% of that population is between 45 and 50 objects. 45 to 50 unknown, untracked, uncatalogued asteroids larger than 1 kilometer in diameter, crossing Earth's orbital neighbourhood on schedules we have no knowledge of, at distances we cannot calculate because we do not know their orbits, with close approach dates in their futures that could be decades away or could be disturbingly soon. These are not hypothetical objects. They exist. They are out there right now, completing their orbits, crossing their paths, carrying the same mass and the same kinetic energy potential as the objects we do know about. The only thing that distinguishes them from the known kilometer-class asteroids is that no telescope has yet captured their light in a way that triggered recognition. They are not safe because they are unknown. They are unknown, and that is a different condition entirely. The large object picture, with its 95% discovery completeness, is actually the reassuring picture. The medium object picture is considerably less so. For asteroids in the 100 to 500 meter size range, objects large enough to devastate a continent, generate tsunamis capable of crossing entire ocean basins, or inject enough debris into the upper atmosphere to disrupt global agriculture for multiple growing seasons. Discovery completeness is estimated at less than 50%, less than half. There are more unknown, potentially dangerous medium-sized asteroids in near-Earth space than there are known ones. The known catalogue is the minority of the actual population. Every risk assessment, every probability calculation, every reassuring statement about the current asteroid threat level is built on a dataset that represents less than half of the objects it is trying to characterize. The unknown half is not zero risk. It is unquantified risk. which from a practical standpoint is worse, because you cannot plan around a threat you cannot measure. The Tunguska event of 1908 offers a calibration point that should be part of every public conversation about asteroid risk and almost never is. On the morning of June 30th, 1908, something entered Earth's atmosphere over a remote region of Siberia and detonated in an airburst explosion that flattened approximately 2,000 square kilometers of forest, felling an estimated 80 million trees in patterns that radiated outward from the explosion point, like a vast silent record of the pressure wave. The object that caused this was estimated at somewhere between 50 and 80 meters in diameter. It did not reach the ground intact. It did not create a crater. It simply released its kinetic energy in the atmosphere above the forest, and the result was a devastation zone larger than a major metropolitan area. If that object had arrived at a slightly different time, on a trajectory that took it over London or Tokyo or New York rather than uninhabited Siberian taiga, the death toll would have been measured in millions. We have no reliable estimate of how many Tunguska-class objects exist in near-Earth space. The answer is certainly in the thousands. It may be in the tens of thousands. We have found a small fraction of them. The Torino Impact Hazard Scale, the system developed to communicate asteroid risk to the public in the aftermath of the 1998 XF11 crisis, represents a genuine and thoughtful attempt to solve a difficult communication problem. How do you translate probabilistic orbital mechanics, a field where the honest answer to almost every question is a probability distribution rather than a yes or no, into language that a journalist can report accurately and a policymaker can act on without either causing unnecessary panic or conveying false reassurance? The scale runs from 0, indicating no hazard warranting public attention, to 10, indicating a certain collision with consequences severe enough to threaten the future of human civilization. In practice, nearly every discovered asteroid receives a rating of 0 immediately upon discovery. Objects that temporarily receive elevated ratings, 1s, 2s, occasionally higher, almost invariably return to 0 within weeks or months, as additional observations refine the orbital solution and eliminate the threatening trajectories from the uncertainty cone. The scale works as designed. It communicates the current state of knowledge about known objects in a format that non-specialists can interpret. But the Torino scale has a structural limitation that defines the outer boundary of what any catalogue-based risk communication system can achieve. It only applies to objects that have been discovered and characterized. An asteroid with no catalogue entry has no Torino rating. It is not rated 0. It is not rated at all because the rating system has no mechanism for incorporating objects that have not yet been found. The distinction between a 0 rating and an unassigned rating matters enormously. A 0 rating means we have looked at this object, we have calculated its orbit, and current models show no meaningful impact probability. An unassigned rating means we have no information about this object. One is a statement of assessed safety. The other is a statement of ignorance. The Torino scale, by design, converts the second category into invisibility. Unknown objects do not appear in the risk landscape because the risk landscape is defined by the catalogue, and the catalogue is defined by what has been discovered. This means the actual risk profile of near-Earth space is systematically and structurally underestimated by any analysis that works exclusively from the known catalogue. The unknown objects are not absent from near-Earth space simply because they are absent from the catalogue. They are present. They are crossing orbital paths. They are completing approaches. Some of them, on some schedules we cannot calculate, are passing within distances that would register as significant if we knew they were happening. The detection gap in the 100 to 500 meter range does not represent a gap in the threat. It represents a gap in our awareness of the threat. Those are not equivalent situations, and conflating them produces a false sense of security that the actual physical inventory of near-Earth space does not support. This is the broader and more unsettling lesson that 1997 XF11 is positioned to teach if we are willing to listen to it carefully. The asteroid itself, in all current models with all current data, is not the primary threat. The impact probability for October 2028 is 0. The existing orbital solution, though aging, places XF11 on a trajectory that clears Earth comfortably. The direct, immediate danger from this specific object in this specific approach is not what should be keeping planetary defense scientists awake. What should be keeping them awake is what XF11 represents rather than what it threatens. It is a mirror. a large kilometer-class orbit-crossing mirror that reflects back at us the precise shape of the gaps in our planetary defense infrastructure. The unmeasured Yarkovsky drift, the decade-old radar solution, the missing characterization mission, the post-flyby orbital uncertainty that nobody is currently funded to resolve, and asks us whether we are satisfied with what we see. XF11 is not the danger. XF11 is the diagnostic. It is a known object with a known approach date and a known set of unresolved scientific questions, arriving at a moment when the technology to answer those questions exists. The scientific understanding of why they matter exists, and the operational response has not matched the intellectual understanding. If the planetary defense community cannot mobilize appropriate attention for a kilometer-class asteroid with a confirmed close approach in 2028, that is not a statement about XF11. It is a statement about the infrastructure, the priorities, and the institutional will that the infrastructure reflects. The question of whether appropriate attention arrives before the October 2028 window closes is not a physics question. Physics does not determine whether a radar campaign gets scheduled. Physics does not determine whether a characterization mission gets funded. Physics does not determine whether the post-flyby orbital uncertainty gets resolved before it becomes consequential rather than merely theoretical. Those outcomes are determined by priorities, the priorities of funding agencies, mission planners, observatory directors, and ultimately the governments and publics that set the boundary conditions within which all of them operate. The capability to do this right exists. The knowledge of why it matters exists. What remains is the will to treat a zero probability event as something worth caring about before the probability changes. Because the time to check the math is not after something moves. The time to check the math is right now, while there is still time to act on what the math reveals. Part 11. The interstellar visitor that changed everything. In the summer of 2025, the sky delivered something that had never been confirmed before. An object was detected approaching the inner solar system, not on any orbit bound to the Sun, not following the curved, gravitationally captive path of a comet or asteroid born in our own solar neighbourhood, but on a hyperbolic trajectory, the distinctive mathematical signature of something moving too fast to have originated anywhere nearby. It was coming from interstellar space, from between the stars, from a region of the galaxy so remote that the Sun's gravity had never touched it, shaped it, or claimed it. The object was designated 3I/Atlas, becoming the third confirmed interstellar visitor ever detected passing through our solar system. And the scientific community's response was immediate, coordinated, and intense in a way that was, to put it with the gentlest possible framing, conspicuously different from anything that 1997 XF11 has ever managed to generate. To understand why that contrast matters, it helps to recall what happened when the first two interstellar visitors arrived. Oumuamua appeared in 2017, detected by the Pan-STARRS Survey Telescope in Hawaii, as a faint, fast-moving point of light on an unmistakably hyperbolic path. Within weeks, it had generated more scientific papers, more dedicated telescope time, more international coordination, and more genuine public fascination than most near-Earth asteroid discoveries manage across their entire observed history. The object's unusual shape, inferred from its dramatic brightness variations as it rotated, its anomalous acceleration as it departed the solar system, its reddish surface colour suggesting long exposure to interstellar radiation, every peculiarity became a scientific event in itself. The second interstellar visitor, 2I/Borisov, arrived in 2019 and received comparable treatment, with the added advantage of being a clearly cometary object that allowed detailed spectroscopic characterization of its composition. Both objects generated the kind of institutional mobilization that planetary defense advocates spend years trying to achieve for orbit-crossing asteroids and rarely do. The logic driving that mobilization is sound and should be acknowledged honestly before the critique begins. Interstellar objects are genuinely extraordinary. They carry chemical and physical information from stellar environments that we have no other way to sample. They represent formation conditions around other stars, potentially other types of planetary systems, possibly other histories of organic chemistry. They arrive once and leave forever. The urgency of observation is absolute and unambiguous in a way that it almost never is for known solar system objects. Observe now or lose the opportunity permanently and irrecoverably. When a one-time visitor crosses through the inner solar system on a trajectory that exits as certainly as it entered, there is no second chance, no subsequent close approach, no opportunity to schedule follow-up observations in a later apparition. The scientific community responds with appropriate urgency to a genuinely urgent situation. That is the system working as it should. But the contrast with XF11 is illuminating in ways that become increasingly uncomfortable the longer you sit with them. 3I/Atlas, like Oumuamua before it, and 2I/Borisov before that, carries an impact probability of exactly 0. By definition, an object on a hyperbolic trajectory is passing through. It entered from interstellar space on a path determined by its velocity and direction, long before it reached our solar system, and it will exit on a path that carries it back out into the galaxy. It is not gravitationally bound. It is not going to hit Earth. It is not going to hit anything in our solar system. The urgency of observing it is entirely scientific, entirely about information gathering, entirely about understanding the cosmos better. These are legitimate and important goals. They are not planetary defense goals. 1997 XF11, by contrast, is gravitationally bound to the solar system. It has a minimum orbital intersection distance with Earth of effectively 0. It is potentially 4 times larger by diameter than Apophis, the asteroid that commands dedicated spacecraft missions and international scientific conferences dedicated to its study. It crosses Earth's orbital path every 1.73 years, has been doing so for an extraordinarily long time, and will continue doing so for an extraordinarily long time into the future. It is making its closest approach in recorded human history in October 2028. Its last dedicated radar campaign was conducted in 2016. Its Yarkovsky drift has never been measured. The post-flyby orbital resonance scenarios that could produce concerning encounters in the 2030s and 2040s have not been resolved with data current enough to fully trust. And it generates, in the scientific literature and in the public consciousness, a level of attention that does not approach what a newly discovered interstellar visitor produces in its first month of observation. The asymmetry is not entirely irrational, and intellectual honesty requires engaging with the reasons before dismissing them. Scientific novelty carries genuine value that is difficult to quantify, but real. An object never seen before carries information that familiar objects cannot provide. The institutional momentum that forms around novel discoveries reflects something real about how scientific knowledge advances. Breakthroughs often come from unexpected objects and unexpected observations, not from continued monitoring of well-characterized ones. The funding structures that support rapid response to interstellar visitors exist because the scientific community has correctly identified these objects as rare, valuable, and time-limited. None of this is wrong. All of it is, in isolation, defensible. What is not defensible is the implicit assumption that scientific novelty and planetary defense relevance occupy separate categories that need not be weighed against each other. Telescopes that are coordinating globally to track 3I/Atlas are telescopes with finite observation time that cannot simultaneously run dedicated radar campaigns against XF11. Scientists writing mission proposals for interstellar visitor characterization are scientists whose professional bandwidth is not being applied to planetary defense characterization. Grant committees evaluating proposals in the same funding cycle cannot fully fund both. The trade-off is real even when it is not acknowledged explicitly, and the human tendency to prioritize novelty, spectacle, and the excitement of the unprecedented over the slow, unglamorous, methodical monitoring of known threats is not a feature unique to astronomy. It is a feature of how human attention and institutional resources are distributed across essentially every domain of organized human activity. We are drawn to new things, we are drawn to unique things, we are drawn to things that have never been seen before. An asteroid that has been in the catalogue since 1997, whose orbit is considered resolved, whose impact probability is 0, this object does not activate the same cognitive and institutional responses as a visitor from another star system, regardless of the relative magnitude of what each object represents as a potential future concern. In most domains, this attentional bias toward novelty produces outcomes that are suboptimal but recoverable. We overfund exciting new research directions and underfund important maintenance and monitoring work and the cost is measured in slower progress and missed opportunities. In planetary defense, the asymmetry between the cost of adequate monitoring and the cost of inadequate monitoring is not symmetric and not recoverable. The suboptimal outcome is not slower progress. The suboptimal outcome is binary. Either a threat is identified with sufficient lead time to respond or it is not. There is no partial credit. There is no remediation. The window for action either exists or it does not, and once it closes, it does not reopen on any human timescale. What the Interstellar visitor story also does, perhaps more valuably than any single scientific result it produces, is reframe what the cosmos actually looks like when viewed honestly from Earth's surface. We tend, in the comfortable routine of daily life, to treat space as a backdrop, a vast, static, essentially empty stage on which human events unfold. The interstellar visitors challenge that picture directly. They arrive from between the stars carrying evidence of processes and environments, operating on scales and timescales that dwarf anything in human experience, and they pass through our solar system as casually as we might pass through an intersection without stopping. Their arrival is a reminder that the solar system is not an isolated, bounded, protected enclosure. It is a region of space embedded in a galaxy full of moving objects, crossing trajectories and gravitational interactions playing out across billions of years. The occasional interstellar visitor is not an anomaly interrupting the normal quiet of our neighbourhood. It's evidence of how dynamic, trafficked and genuinely active our cosmic environment actually is at timescales longer than human memory. Against that backdrop, the question of whether we are adequately monitoring the orbit-crossing asteroids we already know about becomes something more than a technical budgeting question. It becomes a statement about how seriously we take the evidence that the solar system is not a safe and predictable place by default, that the relative quiet of the past few thousand years of human civilization is a contingent condition rather than a guaranteed one, and that the infrastructure we build now to understand and characterize the near-Earth object population is the infrastructure that determines whether future generations have the options we currently have. 3I/Atlas is a messenger from another star system, and the message it carries about the nature of our cosmic environment is genuinely important. But 1997 XF11 is also a messenger. Its message is closer to home, and right now we're not reading it with nearly enough attention. Part 12, The DART Precedent. In September of 2022, humanity deliberately crashed a spacecraft into an asteroid. Take a moment with that sentence, because it is easy to read past it too quickly and miss what it actually represents. This was not an accident. This was not a near miss or an uncontrolled re-entry, or any of the other ways that human-made objects have unintentionally collided with things in space. This was a carefully designed, meticulously planned, years in development planetary defense experiment executed with extraordinary precision, and it worked in a way that exceeded even the most optimistic predictions the mission team had allowed themselves to make publicly. The spacecraft was called DART, the Double Asteroid Redirection Test. The target was Dimorphos, a small moonlet in orbit around the larger asteroid Didymos, selected specifically because the moonlet's orbital period around its parent body provided a measurable before and after comparison that a single isolated asteroid could not offer. Dimorphos was approximately 160 meters in diameter, roughly the size of a large sports stadium. DART impacted it at approximately 6.6 kilometers per second, which is about 19 times the speed of a rifle bullet, and the kinetic energy transferred in that fraction of a second changed Dimorphos's orbital period around Didymos by 33 minutes. 33 minutes, measured precisely, confirmed independently by multiple telescope facilities around the world, reproduced in calculations that matched the observation. The mission did not just succeed, it over-delivered. Pre-mission estimates had suggested an orbital period, change of perhaps 10 minutes, would represent a successful demonstration. The actual result was more than 3 times that. The significance of this achievement is worth sitting with rather than rushing past. For the overwhelming majority of human history, the scenario of an asteroid on a confirmed collision course with Earth had exactly one possible outcome. You could detect it, if you were lucky, and had the technology and the lead time. You could calculate its trajectory with increasing precision as the approach date neared. You could announce the finding to the world and watch the reaction unfold, and then you could do nothing except wait. because the physical reality of a large rock on a gravitationally determined path toward your planet was simply beyond any human capacity to alter. The asteroid would arrive. The only variable was the scale of the consequence. DART changed that narrative in a way that is genuinely historic and genuinely underappreciated outside of the planetary defense community. Not completely. Not for all scenarios and all timescales and all object sizes. But the fundamental question of whether humanity is capable, in principle, of altering the trajectory of an asteroid received a definitive answer in September 2022. The answer is yes. For the first time in the 4 billion year history of life on this planet, a species living on Earth demonstrated the ability to reach out into space and change where a rock is going. That is not a minor footnote in the history of science. That is one of the most consequential demonstrations of technological capability in human history, and it happened with relatively modest resources and received relatively modest attention. The follow-up to DART deepens the achievement rather than simply celebrating it. The European Space Agency's Hera mission launched in October 2024 and is currently travelling to the Didymos-Dimorphos system to conduct the detailed forensic analysis that DART's impact made possible. Where DART was the experiment, Hera is the analysis of the results. It will measure the crater that DART's impact created, characterising its size, depth and morphology in ways that reveal how the asteroid's surface and subsurface responded to the kinetic impact. It will assess changes to Dimorphos's shape and spin state resulting from the impact and the subsequent redistribution of material. It will refine scientific understanding of how kinetic impactors actually work on real asteroid surfaces under real conditions, as opposed to how they work in computational models built on assumed material properties. The gap between modelled behaviour and actual behaviour in complex physical systems is often where the most important scientific discoveries live, and Hera is positioned to explore exactly that gap. The combination of DART's impact data and Hera's detailed characterisation represents the kind of systematic, iterative, build on previous results scientific program that transforms a demonstration into a genuine engineering foundation. Planetary defense is not yet an engineering discipline in the mature sense. DART and Hera together are laying the groundwork for it to become one. But here is the mathematical reality that the justified celebration of DART's success should not be allowed to obscure, because obscuring it creates a false sense of security that the actual physics does not support. Dimorphos, the target of humanity's first asteroid deflection demonstration, is 160 meters wide. 1,997 XF11 is potentially 1,400 meters wide. The kinetic energy required to meaningfully deflect an asteroid does not scale linearly with its size. It scales with mass, and mass scales with the cube of the diameter. Work through the arithmetic. A sphere 1,400 meters in diameter has a diameter roughly 8.75 times larger than a sphere 160 meters in diameter. Cube that ratio and you get approximately 670. Adjust for the fact that XF11's estimated diameter range extends from 700 to 1,400 meters, and you get a range, but even at the lower end of that range, the mass comparison is stark. A 1.4 kilometer object, assuming density comparable to Dimorphos, has on the order of 3,400 times the mass of a 160 meter object. Deflecting XF11 with a DART-scale kinetic impactor would be the physical equivalent of attempting to change the course of a fully loaded supertanker by throwing a tennis ball at it. The tennis ball hits. The supertanker does not notice. Deflecting an object of XF11's potential size would require something qualitatively different from anything DART demonstrated. A much larger kinetic impactor, or more likely multiple impactors working in coordinated sequence, each one substantially more massive and faster than DART. A nuclear standoff detonation, a nuclear device detonated near the asteroid's surface rather than on it, designed to ablate surface material and create a reactive thrust, which remains in the theoretical and early conceptual development stage and carries its own set of political and logistical complications that make it a planning challenge of extraordinary complexity. A gravity tractor mission, which involves a spacecraft flying in close formation with an asteroid for years or decades, using the gravitational attraction between the spacecraft and the asteroid to very slowly, very gently, nudge the asteroid onto a slightly different trajectory. a technique that works only with extraordinary lead time measured in decades rather than years. Each of these approaches represents a different point on a spectrum running from technically feasible with current technology to technically possible in principle, but requiring development timelines that have not yet been seriously resourced. None of them are ready to deploy against a specific threat on any timeline that could be described as near-term. None of them could be made ready quickly if the need arose suddenly. This is where the logic of planetary defense reduces to a single, inescapable principle that the DART mission both illustrates and, if read too triumphantly, risks obscuring. The principle is lead time. Everything in planetary defense is a function of lead time. The earlier a threat is identified, the more options exist for addressing it. With 20 or 30 years of warning, even relatively modest technologies applied consistently over long periods can alter an asteroid's trajectory enough to convert a collision into a near miss. The geometry of orbital mechanics means that a very small change applied very early produces a very large displacement by the time the original impact date arrives. With 10 years of warning, the options narrow but remain meaningful. With 5 years, they narrow further and begin to require capabilities that do not currently exist at operational readiness. With 2 years, the options for a kilometer-class object under current technology are, to be direct about it, essentially non-existent. You cannot build, launch and operate a deflection mission for a kilometer-sized asteroid in 2 years with anything currently in existence or in near-term development. The physics does not care about the budget cycle, or the mission planning timeline or the political process required to authorize a planetary defense response. The physics simply requires that the work be done before it is needed, or it cannot be done at all. DART proved the terminal end of the planetary defense chain, the deflection capability that transforms an identified threat into a manageable problem given sufficient lead time. That is an extraordinary and historic achievement. But the terminal end of the chain is only useful if the front end functions reliably. The front end is detection, tracking, and characterization, finding the threatening object early enough, determining its orbit precisely enough, and understanding its physical properties thoroughly enough to plan and execute a deflection mission with confidence in the outcome. And the front end is exactly where the story of 1997 XF11 reveals the current system's most specific and most consequential limitations. A kilometer-class asteroid with a confirmed close approach in 2028, an unmeasured Yarkovsky drift, a last radar campaign conducted nearly a decade ago, and no dedicated characterization mission in development is not a failure of deflection technology. DART works. The failure mode that XF11 represents is upstream of deflection entirely. It is the failure to maintain the quality and currency of orbital knowledge that makes deflection planning possible in the first place. DART gave us the hammer. The question XF11 is asking is whether we are keeping close enough watch on the nails. Part 13. The new asteroid detection race. The limitations of the current planetary defense infrastructure are not going unaddressed, and that matters enough to say clearly before the complications begin. The scientific and governmental communities have recognized, with increasing institutional seriousness over the past decade, that discovery completeness for medium-sized near-Earth asteroids is insufficient for the level of confidence that genuine planetary defense requires, and that correcting this insufficiency demands new telescope capabilities specifically engineered for the task, rather than repurposed from other scientific programs. The recognition is real. The response is real. The investment, while slower and smaller than the most urgent advocates in the planetary defense community would prefer, is moving in the right direction. Understanding what is being built, why it is being built the way it is, and what it will and will not be able to do by the time 1997 XF11 makes its October 2028 flyby, requires working through both the genuine promise of the new infrastructure and the specific, uncomfortable timing problem that infrastructure cannot retroactively solve. The most important near-term development in planetary defense detection capability is the NEO Surveyor mission, a space-based infrared telescope designed from the ground up for the specific purpose of finding near-Earth objects. NEO Surveyor is not a general-purpose space telescope that happens to be useful for asteroid detection. It is an instrument whose design, orbit, operational cadence, and data processing pipeline were all optimized around the single goal of finding potentially hazardous asteroids as efficiently and completely as possible. NASA approved its development, and it is moving through the construction and testing phases that precede launch. Its planned capabilities, when operational, would allow it to find more potentially hazardous asteroids faster than any ground-based survey system currently operating, and to find categories of objects that ground-based systems miss entirely. The reason NEO-Surveyor operates in the infrared rather than visible light reveals something fundamental about the detection challenge that is easy to overlook. Asteroids are not uniform objects. They vary dramatically in their surface properties, and one of the most consequential sources of variation is albedo, the fraction of incoming sunlight that the surface reflects back rather than absorbing. Some asteroids are highly reflective with albedos comparable to fresh snow. Others are extremely dark with albedos as low as a few percent, absorbing nearly all the light that strikes them and reflecting almost none. A dark asteroid and a bright asteroid of identical physical size present completely different detection challenges to a visible light telescope. The bright one shows up clearly in survey images. The dark one, reflecting perhaps 5% of the light that the bright one reflects, may be completely invisible in the same image, even though it represents an identical mass, an identical kinetic energy, and an identical threat potential. Visible light surveys are systematically blind to dark asteroids at distances where those asteroids would otherwise be detectable. The detection catalogue is therefore systematically biased. It overrepresents bright, reflective objects and underrepresents dark, absorbing ones. Infrared detection breaks this bias. When sunlight hits a dark asteroid and is absorbed rather than reflected, that energy does not disappear. It heats the surface, and the heated surface radiates thermal energy in the infrared part of the spectrum. The amount of infrared emission is related to the asteroid's physical size and surface area, not its reflectivity. A dark asteroid that is essentially invisible to a visible light telescope radiates infrared energy in a way that is directly proportional to how big it is. An infrared survey telescope therefore detects dark and bright objects with comparable effectiveness, producing a catalogue that is far less biased by surface properties and far more representative of the actual physical population of near-Earth objects. This is not a marginal improvement. It is a structural correction to a systematic blind spot in the existing detection infrastructure, and it means that NEO-Surveyor will find objects that decades of visible light surveys have been constitutionally incapable of finding, regardless of how sensitive or well-operated those surveys were. The Nancy Grace Roman Space Telescope adds a different dimension to the improving capability picture. While not designed exclusively as a planetary defense instrument, its primary scientific mission covers a wide range of cosmological and astrophysical questions. The Roman telescope's wide-field imaging capabilities and extraordinary sensitivity will make it a significant contributor to near-Earth asteroid detection as a secondary scientific product of its primary observations. Wide-field, high-sensitivity space-based imaging finds moving objects as a natural consequence of imaging large areas of sky repeatedly, and the Roman telescope's observing program will generate data useful for asteroid detection as a genuine and valued byproduct. On the ground, the Virasi-Rubin Observatory in Chile, with its legacy survey of space and time program, represents perhaps the most ambitious ground-based sky survey ever constructed. Its combination of a very large aperture, an extraordinarily wide field of view, and a cadence designed to image the entire visible sky every few nights will generate a data stream of previously unimagined volume. Petabytes of imaging data per year containing the positional signatures of moving objects that no previous survey had the speed or sensitivity to capture. The Rubin Observatory alone is expected to discover more near-Earth asteroids in its first few years of full operation than have been found in all of the preceding decades of systematic sky surveys combined. The cumulative effect of these new facilities, when they reach full operational capability and their data streams are fully integrated into planetary defense workflows, will be genuinely transformative for the field. Current models suggest that NEO-Surveyor alone, operating over a decade, could take the discovery completeness for potentially hazardous asteroids larger than 140 meters from its current level of below 50% to above 90%. Think about what that transition represents. The population of medium-sized near-Earth asteroids, the ones large enough to devastate a continent or generate globally disruptive atmospheric effects, is currently more unknown than known. Within a decade of NEO-Surveyor's full operation, that population would be more known than unknown by a large margin. The dark, uncharacterized orbit-crossing objects that currently represent unassigned risk in near-Earth space would largely become catalogued, tracked, and assessed entities with orbital solutions, risk profiles, and the long observational histories that allow accurate long-term trajectory prediction. The unknown unknown, the category of threat that cannot be planned for because it cannot even be named, would be substantially converted into the known unknown, which is a category that planetary defense infrastructure is specifically designed to manage. That conversion is not a complete solution, but it is the difference between navigating in darkness and navigating with a map that has most of the relevant features marked. But these facilities are being built now, and the gap between being built now and being fully operational and producing the data that transforms the planetary defense picture is measured in years that matter enormously for one specific reason. The 2028 XF11 flyby occurs within the operational gap. It arrives after the era of the old infrastructure, the ground-based visible light surveys that have served planetary defense since the 1990s, and before the new infrastructure reaches the full operational capability that would make comprehensive characterization of close approaches routine. NEO-Surveyor, depending on its launch timeline and commissioning period, may be operational by the time of the 2028 flyby. But operational and fully calibrated and producing the kind of mature, well-validated data stream that supports high-confidence orbital refinement are different conditions separated by time. The Rubin Observatory will be generating data, but its pipeline for near-Earth object detection will still be in its early operational phase. The Roman telescope's contribution to asteroid detection, valuable as it will be in the long run, is a secondary product of a primary mission with its own scheduling and operational priorities. The asteroid arriving in October 2028 is arriving at a specific moment in the history of planetary defense infrastructure, after the limitations of the old system have become well understood, and before the new system has reached the maturity to fully address those limitations. It is arriving in the gap, and the new telescope era, for all its genuine and justified promise, cannot retroactively improve the data quality for an object that makes its closest approach before that era reaches full operational stride. The orbital solution that will be used to predict the precise geometry of XF11's 2028 flyby, and by extension to determine the post-flyby resonance relationship that governs the asteroid's trajectory for decades afterward, will be built on the data that exists between now and the flyby date. What data gets added to that solution between now and October 2028 is a function of deliberate choices made by specific people with specific resources in specific institutional contexts, not of the new telescopes that are coming, of the existing capabilities that are available right now, and the decisions about how to apply them. The detection race is real, urgent, and moving in the right direction. That statement is true and important and should be said without qualification, because the people building NEO-Surveyor and operating the Rubin Observatory and planning the Roman Telescope's asteroid detection program are doing work that will matter enormously for planetary defense over the decades to come. The timeline of that race, mapped against the specific timeline of XF11's approach, reveals a gap that is narrow enough that it might still be closed with deliberate action taken now. A radar campaign, an updated orbital solution, a small characterization mission if the planning could somehow be accelerated. The window has not closed, but it is closing in a way that the new instruments cannot address on the relevant schedule. What happens in the gap between the infrastructure we have and the infrastructure we are building is not determined by technology. The technology exists. It is not determined by scientific understanding. The understanding exists. It is determined by choices, specific, identifiable, still reversible choices about where to point existing telescopes, how to allocate existing radar time, and whether the oldest question in planetary defense still has the same answer it has always had. Are we watching closely enough? The new era will make that question easier to answer, but the new era has not arrived yet, and XF11 is not waiting for it. Part 14. Artificial intelligence is now searching the sky. The volume of data that modern sky surveys generate is difficult to hold in the imagination without some kind of anchoring comparison. A single night of operation at the Vera C. Rubin Observatory produces approximately 20 terabytes of imaging data. 20 terabytes in a single observing night, every clear night, across a survey program designed to run for a decade. The accumulated dataset over the full operational lifetime of the Rubin program will dwarf the entire history of photographic and digital astronomy combined, by orders of magnitude that make the comparison almost meaningless. Every frame in that dataset contains thousands of faint points of light. Some of those points moved slightly between exposures. A small fraction of the moving points are near-Earth asteroids, objects crossing their orbital paths, making their quiet approaches, carrying their masses and their velocities through a region of space that intersects with Earth's orbital neighbourhood. Finding those objects in that dataset is not a problem that human reviewers can solve. The numbers are simply too large, the signals too faint, the rate of data production too continuous. The solar system's asteroid population is embedded in the data the way individual voices are embedded in the roar of a stadium crowd. You cannot pick them out by listening harder. You need a different kind of tool entirely. That tool is machine learning, and its application to asteroid detection has advanced further and faster in the past decade than most people outside the field realize. Artificial intelligence systems trained on existing asteroid observations, tens of thousands of confirmed detections spanning decades of sky survey data, can now identify candidate moving objects in telescope images with accuracy that approaches, and in several specific performance metrics actually exceeds, the accuracy of human expert reviewers doing the same task. This is not a claim about general intelligence or about machines replacing scientists in any broad sense. It is a much more specific and more interesting claim, that for the particular task of distinguishing a real faint moving object from the various categories of noise and artifact that appear in astronomical images, trained neural networks have reached a level of reliability that makes them not just useful but essential. The algorithms have learned to recognize the difference between a genuine asteroid detection and a cosmic ray hit on the sensor, a satellite streak crossing the frame, a diffraction artifact around a bright star, a hot pixel misfiring in the detector array. They make these distinctions consistently, at speeds that no human team could match, across data volumes that no human team could process. The practical operational consequence of this capability is significant. The same volume of sky that a team of human reviewers might work through over several weeks can now be processed in hours. Candidate objects are flagged automatically as the data arrives. Positions are measured with software that applies the same algorithms consistently across every detection, rather than varying with reviewer fatigue or attention. Preliminary orbital solutions are calculated from the flagged detections and cross-referenced against existing catalogues to identify potential matches with known objects or flag genuinely new discoveries. Follow-up observation priorities are assigned based on the preliminary orbital solutions, routing the most urgent cases, objects with high uncertainty or close approach dates, to available telescope facilities for additional observations before the discovery window closes. The entire front end of the asteroid discovery pipeline, from raw imaging data to actionable follow-up priority list, is now substantially automated in modern survey operations, and the automation is good enough that the bottleneck has shifted from data processing to follow-up observation capacity. That is a remarkable transformation from the situation of even 15 years ago, when human review of survey images was a genuine limiting factor in discovery rates. Beyond processing new observations as they arrive, artificial intelligence is being applied to something that may ultimately be even more valuable for planetary defense. The vast archives of old astronomical data accumulated over decades of sky survey programs before the current generation of automated systems existed. Those archives, now largely digitized and increasingly accessible through centralized repositories, contain the photographic and early digital signatures of asteroids that were present in the images at the time of observation, but were never recognized as asteroids because the tools and workflows needed to identify them did not yet exist. The sky has been watched for a long time. Much of what it contained during that watching was not understood until later. Systematic AI-assisted searches through historical sky survey archives have already produced pre-discovery observations of known objects, detections that extend the observational arcs of catalogued asteroids backward in time, improving orbital solutions in exactly the way that the 1990 Palomar plates improved the orbital solution for XF11 during the 1998 crisis. The difference is that in 1998, the archive search was reactive, triggered by a specific alarm, conducted under time pressure, dependent on someone thinking to look. The The AI-assisted archive mining now underway is systematic and proactive, working through historical data methodically rather than waiting for a crisis to motivate the search. The archival rescue that saved the XF11 orbital solution, through a fortunate combination of luck and good record-keeping, is being institutionalized as a standard scientific practice rather than remaining a contingent emergency response. The implications of population-level machine learning analysis extend the value of these tools beyond individual asteroid discoveries and orbital refinements. When AI systems analyze the statistical properties of the discovered near-Earth asteroid population, size distributions, orbital distributions, composition proxies inferred from color and spectral data, the correlations between these properties across thousands of objects, they can use those patterns to characterize the properties of the undiscovered population as well. The discovered sample, while incomplete, is not random. It has biases that are themselves informative. Objects that are easier to detect are overrepresented. Objects that spend more time in geometries favourable for observation are overrepresented. By modelling these observational biases and their effects on the detected sample, machine learning analyses can infer what the full population must look like in order to produce the detected sample we actually observe. The uncertainty about what we have not yet found is being converted from an open-ended, unquantifiable gap into a statistically characterized distribution with error bars and confidence intervals. That is a meaningful advance. You can plan around a quantified uncertainty in ways that you simply cannot plan around an unknown one. None of this, stated honestly and completely, makes the specific situation of 1997 XF11 less relevant or less urgent. The value of AI-assisted sky survey processing is real and significant for the overall project of cataloguing the near-Earth asteroid population. It does not substitute for a dedicated radar campaign against a specific known object with a specific known close approach date and a specific well-documented set of physical properties that have not been adequately characterized. The broad, population-level, statistically powerful AI survey approach is designed and optimized for discovery, for finding new objects and building the catalogue. What it is not designed for, and what it cannot be repurposed to accomplish without fundamental changes to the underlying approach, is the targeted, high-precision, physically detailed characterization of a specific known asteroid whose orbital solution is aging, and whose post-flyby trajectory depends on parameters that have never been measured. These are complementary capabilities operating at different levels of the planetary defense problem. The AI era makes the overall picture significantly better. It does not reach into the specific gap that XF11 represents and close it, because the gap is not about survey coverage or catalogue completeness. The gap is about the depth of knowledge for a specific object that is already in the catalogue and has been there for nearly 30 years. The broader transformation that AI is enabling in astronomy does, however, change what is possible with the data that already exists for XF11. And this is worth examining carefully, because it represents an opportunity that may not be fully exploited. Archive mining algorithms of the kind now being applied systematically to historical sky survey data could be applied specifically and deliberately to the full historical record in search of additional pre-discovery observations of XF11 that have not yet been identified. The 1990 Palomar plates were found in 1998 because someone thought to look manually in a specific archive under time pressure. The question of whether additional observations of XF11 exist in the decades of sky survey data accumulated since then, data that was not specifically searched for XF11 at the time it was collected, is a question that modern AI-assisted archive mining is positioned to answer more thoroughly than any previous search could have managed. Finding even a small number of additional historical observations could extend the orbital arc further, tighten the existing solution, and reduce the uncertainty in the post-flyby trajectory prediction in ways that matter for the 2037 and 2040 resonance scenarios. Beyond archive mining, orbital refinement algorithms applying modern statistical and computational methods to the existing observation dataset for XF11 could extract more precise orbital parameters than the classical methods used when those parameters were last seriously updated. The observations exist. The data has been collected over more than 3 decades. What has changed since the last serious orbital solution was computed is not the observations. It is the sophistication of the algorithms available to analyze them. Applying current best practice orbital determination methods to the full existing dataset including all observations recorded since the 2016 radar campaign, could improve the orbital solution meaningfully without requiring a single new observation to be taken. That improvement would not be as valuable as a fresh dedicated radar campaign, generating new high-precision positional data. It would not characterize the Yarkovsky drift or measure the spin state, or reveal the surface composition. But it would be something concrete, achievable with existing resources, applicable to the specific problem, and improvable in a situation where every reduction in orbital uncertainty matters for what comes after October 2028. The technology to do this is available. The data to do it with exists. The question that remains, as it so often does in this story, is whether anyone is applying it to this specific problem with the urgency that the timeline, quietly and without fanfare, continues to demand. Part 15, The Real Question, F11 leaves us with. Here is where we return to where we started, December the 6th, 1997. A telescope in Arizona, operated by a careful and methodical astronomer doing the slow, unglamorous work of scanning the sky for faint moving points of light. A new dot appeared where no dot had been catalogued before, a mountain-sized rock crossing Earth's orbital path, unknown to every human being who had ever lived until that specific moment on that specific night. 1997 XF11. It caused a brief global panic in March of 1998, when preliminary orbital calculations suggested it might pass dangerously close to Earth in October 2028. It was resolved within 24 hours by the fortunate survival of photographic plates from a routine sky survey conducted 8 years earlier for completely unrelated reasons. It faded from public awareness almost as quickly as it had entered it. And on October 26th, 2028, it is coming back, closer than it has ever come in any moment of recorded human history, travelling at tens of kilometres per second through the inner solar system, bright enough to be visible in amateur telescopes under dark skies, interacting gravitationally with Earth as it passes in ways that will alter its own orbital path for decades to come, and then continuing outward on a slightly modified trajectory that will carry it toward orbital resonance relationships we have not fully characterized with data current enough to place complete confidence in. The story that began with the discovery in 1997 is not finished. It is arriving at a chapter that nobody has adequately prepared for. The current impact probability for the 2028 flyby is 0. That statement deserves to be made clearly, completely, and without the kind of hedging that would allow it to be misread as anything other than what it is. 0. Not negligible, not vanishingly small, not 1 in 10,000 or 1 in a million or any other fraction that could be rounded toward alarm. 0. The existing orbital solution for XF11, built on more than 2 decades of observations that include a dedicated radar campaign conducted at Goldstone in 2016, shows the asteroid missing Earth by approximately 929,000 kilometers at closest approach. That is a comfortable margin by any reasonable standard. Nobody in the planetary defense community is privately alarmed about the 2028 flyby, while maintaining public reassurance as a matter of institutional policy. The scientific consensus is genuine. The reassurance is earned. 2028 is safe. Let that be the foundation from which everything else in this conclusion is built, because what follows is not an argument that the foundation is wrong. It is an argument about what the foundation does not tell us, and why that matters more than the foundation itself might suggest. What this entire story has been about from the moment James Scotty found that new dot in the Arizona sky is the difference between two things that sound similar but are not the same. The difference between knowing that something is safe and knowing why it is safe with the precision that future safety actually requires. The 2028 flyby is safe. The orbital solution says so clearly, and the scientific community endorses that conclusion without reservation. But what happens after the 2028 flyby is a different question, and it is a question whose answer depends on the precise geometry of that flyby, which in turn depends on an orbital solution that is now approaching a decade old at the moment of the approach it is being used to characterize. That solution incorporates a Yarkovsky drift component that has never been directly measured for this object. It does not have a dedicated characterization mission in development or a radar campaign formally scheduled. The post-flyby orbital evolution of XF11, the question of which resonance relationship develops between this asteroid and Earth's orbit after October 2028, and what that resonance implies for the nature of encounters in 2037 and 2040 and beyond, cannot be answered with the confidence that the safety of future generations deserves without data that does not currently exist, and, at the present pace of institutional prioritization, may not exist by the time it becomes consequential rather than merely theoretical. This is a solvable problem, state that equally clearly, because the point of identifying a problem is not to generate helpless anxiety, but to motivate the specific actions that address it. The tools required to solve this problem exist and are operational. The Goldstone Solar System radar can conduct a dedicated campaign against XF11 during the 2028 approach window, generating positional data precise enough to dramatically tighten the orbital solution and producing the physical characterization data, shape, spin rate, surface properties, that feeds directly into Yarkovsky drift modelling. Optical observatories around the world can contribute additional positional observations that further refine the orbit using existing facilities requiring no new development. A small spacecraft mission, not a deflection mission, not a sample return, simply a flyby observer carrying cameras and basic instrumentation, could be dispatched to rendezvous with XF11 during the 2028 approach, taking advantage of the favourable orbital geometry that a close Earth approach creates for mission planning, and returning the kind of detailed physical characterization that no ground-based observation can match. The cost of such a mission, measured against planetary defense budgets and against the scale of what XF11 represents as a physical object, is modest. The scientific and safety value of the data it would return is substantial and durable. It would inform orbital predictions not just for the next decade, but for the century-scale evolution of this asteroid's path through the inner solar system. The technical feasibility is not in question. What has been lacking, specifically and identifiably, is not capability. It is prioritization. The institutional decision to treat the long-term orbital characterization of a known kilometer-class asteroid as urgent enough to resource and schedule and execute, even in the absence of an immediate impact probability that would generate the kind of alarm that forces action. The XF11 story is, at its core, a story about something much more fundamental than asteroid orbital mechanics. It is a story about how human attention and human institutions allocate resources in response to diffuse, long-term, non-immediate risk that is real and characterized and scientifically understood, but that does not present itself as a crisis demanding response on any particular Tuesday morning. Humans are not naturally well calibrated for this category of threat. The cognitive and emotional architecture that our species developed over hundreds of thousands of years of evolution is exquisitely tuned for immediate, concrete present danger. The saber-toothed tiger in the cave entrance, the rival group approaching across the valley. The asteroid that preliminary calculations suggest might hit Earth within the next 30 years, announced in a press release on a specific date, generating headlines and congressional hearings and funding commitments. These are the threats that activate the systems our biology and our institutions are designed to respond to. What does not activate those systems with comparable force is the slow accumulation of uncertainty. The orbital solution that was adequate 5 years ago and is slightly less adequate today, and will be meaningfully less adequate in 2 years. The Yarkovsky drift parameter that sits in the models is an assumed value rather than a measured one, silently introducing error that compounds over decades. The monitoring gap that is not producing any observable consequence right now, and therefore generates no alarm right now, even though the window for addressing it before it matters is measurably and irreversibly closing. The psychological architecture that kept our ancestors alive on the African savanna is genuinely not the architecture that planetary defense requires, and building the institutional structures that compensate for that mismatch, that treat future safety as a present obligation rather than a future problem, is the actual challenge that XF11 is presenting. What 1997 XF11 leaves us with, as it completes its current orbit and begins the approach that will bring it closer to Earth than it has ever come in human memory, is a question that extends far beyond this particular asteroid and this particular flyby date. It is a question about the kind of civilization we are choosing to be on this small, specific, irreplaceable rock in the outer arm of an ordinary spiral galaxy. In 30 years, building from essentially no systematic knowledge of the near-Earth asteroid population, human civilization constructed a planetary defense infrastructure that identified the vast majority of large near-Earth asteroids, demonstrated the ability to physically alter the trajectory of one, and developed the theoretical and technical foundations for addressing future threats given adequate lead time and adequate will. That achievement is genuinely remarkable and genuinely underappreciated. It represents one of the most consequential expansions of human capability in the modern era, accomplished with relatively modest resources and sustained over decades across changing political priorities. It deserves recognition before the remaining gaps are catalogued, and yet the gaps are real, specific, and identifiable. The Yarkovsky drift for XF11 has not been measured. The post-flyby resonance relationship has not been characterized with current data. The 2028 flyby, which represents the best opportunity in any human lifetime to comprehensively understand this object's long-term orbital behavior, is approaching without the dedicated observational campaign that its scientific and safety significance warrants. The knowledge of what needs to be done exists. The capability to do it exists. What remains is will, the collective, institutional, political expression of the judgment that long-term orbital safety is worth investing in before it becomes an emergency. That the uncertainty of the future is a present responsibility rather than a future problem. That checking the math once was a beginning and not a conclusion. The cosmos does not negotiate. It does not adjust its schedule to accommodate budget cycles. It does not pause an asteroid's orbital evolution while institutions complete their planning processes. It does not provide second chances calibrated to the timelines of human decision-making. The rocks continue their orbits with complete indifference to whether we are watching carefully or not. What changes is not the universe. What changes is whether we, the only species in the known history of this planet capable of understanding these threats and potentially redirecting them, choose to exercise that capability with the consistency and foresight that the scale of the responsibility actually demands. 1997 XF11 will make its closest approach on October 26, 2028. It will pass. It will alter its orbit slightly. It will continue outward into the solar system on a path that the next decades will gradually reveal. The question it is asking as it comes, silently, at 20 kilometers per second, with the complete indifference of a rock that has been following its orbit for millions of years before any human was watching, is not whether the current math says we are safe. We know the current math. The question is whether we are the kind of civilization that checks the math once and considers the matter settled, or the kind that understands that the math requires tending, that safety is not a conclusion but a practice, and that the moment to act on that understanding is always, without exception, before the window closes rather than after.